Okay, I think it's about time to start this session. Okay, I'm In Tae-yu from SKKU in Korea, the convener of this plenary session. In this session, we will have two plenary talks about the neutrino oscillations. The first speaker is Dr. Atsuko Ichikawa from Tohoku University. She will talk about the current status and prospects of neutrino oscillations. Dr. Ichikawa, please start.
Okay, thank you very much. Thank you very much for these opportunities. Yeah, I hoped that I can visit the Korea, but this time we cannot. Maybe sometime in future we can meet in person. So my title is Neutrino Oscillations, and I will talk about the current status and the prospects. But there's a wide range of the topic in neutrino oscillations. So in this talk, I will concentrate on the current status and the prospects of accelerator-based long baseline experiment. Sorry for not covering all, but my plan is to concentrate on this part. And so just this is a reminder of the what is the type of the neutrino. Probably you know already very well, but this just a reminder. I will start from this. So how we distinguish the type of the neutrino, it depends on the how do they interact with matters. So some neutrino change it to the electron, and another neutrino changes to a muon when it interacts with matter, and some go to the tau, and we named according to that. So we named that neutrino which changes by the charge of current interaction to an electron as electron neutrino, and the same for muon neutrino or tau neutrino. This is the definition of the flavor or type of the neutrino. And so for a long time, it was believed that the electron neutrino only changes to electron, never into muon or tau. But this is just before the neutrino oscillation was found. And actually, what the nature is more complicated, or So we know that there are three types of charged leptons distinguishable only via mass. E mu tau can be distinguished by only via mass. And then we found three types of neutrino which corresponds to each of E, electron, muon, or tau. And this is distinguishable via interaction with matter. But if neutrinos have masses, there is no need for three types of flavor to be equal to mass eigenstate. So electron neutrino can be a superposition of these three types of mass eigenstate, nu1, nu2, nu3. And actually, we know that the same thing is happening for quarks. So up quark partner is not a down quark, purely a down quark, but down quark, strange quark, and bottom quark superpositions. And then, if eigenstates are different between flavor and mass, then when neutrino is produced, it is produced as an eigenstate of one flavor, so it can be, in case of the two mass eigenstate, it can be written like this, but it travels with different speed. And so after traveling very, very long distance, the superposition is changed. And at the beginning, if it is muon neutrino, then it changes to the tau neutrino here, and then coming back to muon neutrino in such a way, because of this interference, neutrino flavor can change while they are traveling. This is the neutrino oscillation, and in case of the two flavor neutrino oscillations, it can be the probability of observing different type of neutrino can be written like this. And actually, and the neutrino certainly interact with matter and we can detect it, but it's really very rare. For example, for the accelerator produced neutrino has an energy of around 1 GeV, then their mean free path is roughly 10 to 8 kilometer, 10 to 8 kilometer, which corresponds to the distance between solar and Earth. So if we certainly capture the neutrino, we need a solar Earth system size detectors. And for solar neutrino or reactor neutrino, it is much worse. So for 1 MeV neutrinos, they can travel without interacting even 100 light year in the concrete wall or water or materials. So it's really difficult to catch these neutrinos. And the experimentalists succeeded to measure all these neutrinos after the many efforts. So we know many things already from these measurements. And from solar neutrino or reactor neutrino, we know that the difference of the mass square between M2 state and M1 state is about this region. And from the atmospheric or accelerator or reactor neutrino, we know that the absolute value of the M3 square minus M2 square is these numbers. The two orders are bigger than delta M21 square. And from the cosmic microwave background, the baryon acoustic oscillations, the cosmological measurements, there is a upper limit of the neutrino mass that sum of the neutrino is 0.18 electron volt. It is smaller than this one. So from this information, if the order of the neutrino mass is M1, M2, M3, then they would have a masses like this one. And if the order is different, inverted, M3 is lightest, then the neutrinos can have this kind of masses. So anyway, it is around the 0 to 70 milli electron volt masses they have. And also we know how flavor and mass eigenstate are mixing. So left side shows the case of the quark part. Quark mixing matrix, the size of the mixing looks like this, but we know that for the neutrino, it mixed very much, large mixing is observed for the neutrinos. And actually, if written in numbers, it looks like this one. And so certainly we believe that there is some reason why quark mixing matrix is very close to the unit matrix. For the neutrino, it may just a random number, or it may come from some symmetry, like a case of the quarks. So some symmetry is, if some symmetry is assumed in the gut or theory or something, then this kind of mixing numbers, mixing are predicted. So it's close, not the same, but the close. So it may have some meaning. And also, another thing is that the grand unified theory generally prefer normal mass ordering. So by measuring these mixing matrix precisely or determining the mass ordering, we can get some information or hint for the very high energy physics like gut. Yes. And the remaining most important feature of this mixing matrix is that because there are three types of the neutrinos, like the case of the quark, it can have one CP phase in addition to three mixing angles. So usually we use this format for this mixing matrix, and here we have a CP phase. And if it is not 0 or pi, then this changes the phase of the wave function oppositely for particle and antiparticle. So this can cause the CP violation phenomena. Yeah, CP can be violated if here we have a non-zero delta, non-zero or non-pi delta. And this is related to, yeah, this is very much attracted many people because this may be related to the one big mystery that why our universe has only matter and does not have antimatters. So in order to explain the current universe, there must be CP violation, which causes tiny or 10 to the 10th number difference between particle and particle in early hot universe. And we know that the quark violates CP symmetry, and their phase, Dirac CP phase, is 60 degree to 70 degree. This looks large, but cannot explain matter dominant universe, we know. And another type of CP violation, we know that the strong CP is very much small. We don't know the reason, but it seems it is very small. And how about the lepton case? This is what we want to measure by the neutrino oscillation right now. And this delta is actually delta CP phase is actually depend on the definitions where we put it on in the three mixing matrix. And more general way to quantize the size of the CP violation, we can use the Yarskov invariant, so-called. And it is defined like this way with mixing angles. And then we can compare the size of the CP violation between quark and quark and lepton. And the quark case, this Yarskov invariant is 3 times 10 to the minus fifth. It's very small because of the small mixing angles. And on the other hand, in the lepton case, mixing angles, we know that these are the large. So it can be currently explained like this one. So if sine delta CP is close to 1, then CP violation in neutrino can be maybe 3 orders of magnitude larger than the quarks. And there are a number of theoretical models which explain the matter-antimatter asymmetry in universe by this CP violation. There could be a different CP violation, and we cannot distinguish which one is really caused this asymmetry, matter-antimatter asymmetry. But at least, if we can show that this Yarskov invariant is larger than certain value, we can say that there exists a CP violation which is large enough to produce this matter-antimatter asymmetry in universe. And how we measure it? In the neutrino oscillation, so in case of the there's only 2 neutrinos, it will oscillate like this. But if there are 3 neutrinos, because of the complicated interference of, so depending on the value of delta CP, neutrino and antineutrino can oscillate differently. And I myself is now working on the T2K Tokai to Kamiyaka experiment as a spokesperson. So I will start from this T2K experiment. So we produce accelerator, using accelerator, we produce muon neutrino at here, this east side of Japan. And then it travels across the Japanese island and detected by the super Kamiyaka, which located Kamiyaka in Japan. And it's roughly 300 kilometers away, but still so roughly 1 neutrino per square centimeter per second neutrino penetrates super Kamiyaka. And this is the component of the long baseline neutrino experiment. So accelerator, a proton is accelerated and target and interact with target here and produce pion. And these either pi plus or pi minus are focused by these experiments. And in case of the pi plus, it will produce muon neutrino. And in case of pi minus, it will produce anti-muon neutrino beam. So we can switch the neutrino or anti-neutrino beam here. And then it is detected by near detector and the far detector. So the horn looks, the focusing horn looks like this. And this is a view of the decay volume where pion decay to the muon and muon neutrinos. And this is the we have near detectors in the this accelerator site and measure the flux, flavor, energy, and neutrino nucleus interactions before oscillation. And far for per detector, this is the super Kamiyaka detectors, and it is roughly it has a 50 tons of water inside, and among which roughly 23 kiloton is the fiduciary volume, and it is covered by 10,000 20-inch photomultiplier tubes, and it has an excellent performance at the sub-GeV neutrino, which our neutrino beam very much match these energies. And after filling the water, it looks like this, and the neutrino, if interact inside the target, so they will produce either the electron or muon, depending on their type. And this SK, super Kamiyaka, can distinguish electron and muon with very good performance. Muon has a sharp edge of the Cherenkov light, but while the electron, they suffer multiple scattering or the Bremsstrahlung gammas, so it has a fuzzy shapes. And at the beginning of the T2K, T2K started in 2010, but after the 2 or 3 years of 2 years running, T2K observed the 28 events of the electron-neutrino appearance with this significance. And this is the first time neutrino appearance in the oscillation is confirmed. And this has a very important meanings. So we know that muon neutrino almost 100% disappear at the right energies, and most of them go to the tau neutrinos and invisible because the tau is too heavy to be produced. But this time also we know that because of the solar and reactor experiment, only very small fraction, 0.1% of the muon neutrino oscillate to electron neutrino. But by the observation of the electron neutrino appearance, we confirm that there is this oscillation. Then interference between these two oscillations, two oscillation mode, causes the sine delta CP dependent oscillations, and that is how CP violation appears. So the electron neutrino appearance opens the way to measure the neutrino CP violation. Yes. But there is some complexity of the experiment. So neutrino travel inside the Earth, but the Earth is not symmetric about the flavor nor CP. And so electron neutrino and muon or tau neutrino feels different potential inside the Earth, and also neutrino and antineutrino also feel the different potential. And this matter effect is larger for higher energy or longer distances. And this effect is opposite depending on the mass order. So there's some complexity exists. And then it's very good that we have another experiment in the world at different baseline, that is 800 kilometers. The NOVA experiment is running. This is using the NUMI beam from the Fermi main injectors. And here is a comparison of the two experiments. Yeah, so the baseline length is very much different, and the energy corresponding oscillation energy is also different. So matter effect is for 3 times larger for NOVA experiment, and the detector size is similar or a bit super K is larger, and we are running this way. And these two experiments is currently running in the world. So T2K started in 2010, but NOVA started in 2014. But NOVA has increasing power of the beam. So currently we are in a good competition and also a good friendship because of this complementarities. From here, I will talk about the latest result of these two experiments. So this is the muon neutrino disappearance result. So this is a energy spectrum detected at the power detectors for muon neutrino, antineutrino for T2K experiment, and for the NOVA experiment, same way. And so this disappearance probability is very much sensitive to the theta 2, 3 and delta m square. And using these data, this is the allowed region of the theta 2, 3 mixing angle and delta m square. So this black line is NOVA experiment latest result, and this one is the Kitsuke latest result. So plot size are changed to give same scale. Yeah. And super K also has a measurement of using atmospheric neutrino, and it is like this. So all experiment is consistently pointing at the same regions. And Kitsuke also is conducting comparison of the disappearance for neutrino and antineutrino. And CP violation will appear only for appearance. And if we observe only disappearance, it should be exactly same as far as the CPT theorem based on the CPT theorem. So if we observe the difference, then it violates CPT. And actually, we this is the neutrino result, and the larger circle is the antineutrino result. So it is consistent. Yeah, certainly this is unlikely to happen. CPT should be conserved, but neutrino mass may be related to physics at very high energy. So it is worth to check. And actually, we are seeing the consistent result. And for the electron neutrino appearance, so this is the left one is the Kitsuke result, and right one is the NOVA result. And so NOVA case, they observe 4 sigma evidence of the anti-electron neutrino appearance. And Kitsuke, its anti-neutrino data is too small to say such a things. And so this is the allowed region from Kitsuke, allowed region without using the reactor constraint on the theta 1, 3 squares. So you know that so in the Korea there's a Reno experiment, and in China another experiment also there happens diabe or double show experiment. They measure the theta 1, 3 very precisely, and if we don't use that one, the allowed region looks like this delta CP by sine theta 1, 3 squares. So these regions, depending on the mass order, are allowed. And if overlay the reactor measurement result, this region it is constrained in these regions. And once if we use this constraint, next page shows the allowed region with reactor constraint on delta CP versus sine theta 2, 3. Yeah. Then if we use reactor constraint, our result becomes sensitive to the theta 2, 3 versus sine delta. And in this plot, already a T2K result and NOVA result are overlaid. And this also super K result is overlaid. And these line part corresponds to the CP conserving part, and the other regions, CP is violated. There's a question, and but maybe later I will go back. Yes, okay. So, and we actually this plot shows that so if just hand draw the overlap region, these regions are allowed. So yeah, it's very interesting that combined joint analysis would be very important to pin down the allowed oscillation parameters, including delta CP. And this is a delta chi-square for the CP violation. So T2K result, this is normal mass ordering and inverted mass ordering. So T2K result disfavors CP conserving case at the 2 sigma level currently. And there is a group conducting the global fit for all these data. And according to them, no T2K and NOVA result, this is as a function of delta m squares for inverted and normal. The chi-square behave like this. And it seems that normal is disfavored a little bit, but another constraint for the reactor is placed here. So reactor, in order to be consistent with reactor measured delta m square, then normal mass ordering would be is more preferred, and this is a real result of such a global fit. Normal mass ordering as a function of delta Cp and inverted go displayed by this level. It's not so significant yet, but once the SK super K atmospheric result is combined, then inverted mass ordering is disfavored by more strongly. This is the current status, and so I will briefly go to the prospect. So NOVA and TSK will continue data taking a few years, and the beam intensity improved, and TSK will upgrade near detector and power detector, and NOVA will have a test experiment, and these experiments may confirm the CP violation at 3 sigma confidence level, and but the next generation experiment with waiting for the hyperkamiokande in Japan is aiming to start in 2027, and in US, Dune experiment is also in a similar time scale. They are trying to start with a big liquid argon detector and higher beam powers. So physics target is similar between the Dune and the US, but the CP violation is one of the most important one. So this is the summary. So CP violation in quark sector is too small to explain our matter universe, and so large mixing in the lepton sector or large CP violation, and this CP violation is accessible by accelerator long baseline neutrino oscillation experiment, and the T2K may be seeing CP violation or may not. It's for us it's a very exciting time how our data evolves, and and also the next generation experiment hyper-K and Dune will have a high statistics, and so CP violation will be certainly explored with high sensitivity, but they are also aiming to determine its size, so they can discuss the relation with the matter antimatter asymmetry in the universe. Thank you very much. That's all from me.
Thank you for the nice presentation on the status and prospect of neutrino oscillation measurement. Okay, is there any question or comment? Actually, there is one question from Jiajun Zhang. Actually, he posted his question. And in terms of measuring neutrino oscillation, comparing Diabae and Juno, what is the difference for T2K? That's the question.
Measuring nutrition comparing to Diabae and Juno. Diabae and Juno. Okay, so Diabae and Juno is measuring anti-electron neutrino disappearance. Okay, and so how to say? Sorry, for in these figures, so this is a case of the muon neutrino, but if one is just measuring the disappearance, it is a sum of the electron appearance and tau appearance. So in case of the Diabae or Juno experiment, it's also same that they are measuring the anti-electron disappearance. So they can determine that it disappears, but they cannot determine whether how much oscillated to tau neutrino and how much oscillated to muon neutrinos. So they are so that fraction depends on the CP phase. So they are not sensitive to the CP phase, but they can purely measure the overall oscillation probability. So it's really a complementary to the accelerator-based experiment.
Okay, thank you. And there is another question from McCarthy Masood. There is a slight tension between T2K and NOVA in estimating the allowed region of delta Cp. Could you kindly make a comment on the status to address this tension?
Yes, but yeah, so whether yeah, it's whether it should be a okay. So this is, some people say that this is tension. So blue one, so delta CP versus theta 2 3, blue one is the T2K result, and the red one is NOVA result. So in case of the inverted, there's a big overlap. And in case of the normal mass ordering, still there is an overlap. This is a 90% confidence level. So, and sorry. Yeah, so certainly there is an overlap. So I think at this moment, it is not so much a tension, but we can really have a good sensitivity to resolve. It's very good to resolve the degeneracies amongst oscillation parameters.
Okay, thank you, Dr. Ichikawa. There is another question from Sergey Petkov. He said, okay, when there will be a new release of data from T2K and NOVA?
I don't know, but probably the natural place for the next release would be Neutrino conference in 2022. So that is in Korea, right? Yeah. So
Yes.
I guess that is the natural place. Yes.
Okay, thank you. So, other question or comment? Okay, so let's thank the speaker again. Thank you. Okay, so I think, so okay, so we will have a next presentation. The next speaker is Dr. Alexey Similanov from Max Planck Institute. He will talk about the recent developments in neutrino oscillation physics. Dr. Similanov, please start.
Okay, thank you. So you see here in this right-handed photo, Heidelberg, where next PASCOS conference will held. So this is setup of oscillation story. We have the source of neutrino. We describe propagation of neutrino by wave packets of the eigenstates of propagation in vacuum. Those are mass states. Neutrino oscillations are driven by phase difference change between the eigenstates. And if the distance between source and the detector is big enough, there is effect of separation of wave packets due to different group velocities, which leads to a loss of the coherence. Between the source and the detector, one should take into account medium and neutrino interaction with medium, which actually includes wave. Recall that neutrino masses are produced by interaction with a scalar field, which has a wave. Then usual matter, then one can imagine various condensates, classical fields, and new particles, dark matter. So this is landscape of recent studies. And it includes challenges to the theory, which actually covers reformulations, reinterpretation of neutrino oscillation theory, improvements, corrections, etc. It also includes changing of evolution equation due to, for instance, Lorentz invariance violation, change of metric, equivalence principle violation. People studied oscillations at extreme conditions, high and very low densities, high and very low energies, dense, medium, dense neutrino background.
Excuse me.
And of course, people are studying effects of new interactions, non-standard interactions, long-range forces, interactions with dark matter.
Excuse me, Dr. Similanov. The slide didn't change. So we...
So it seems now I cannot change the slides from my.
Yeah, you can just tell us, next page.
Yeah, next
page.
please.
So,
yeah.
Yeah, next please.
Yeah. So, and you hear me, okay? So just repeating that this is the setup of this oscillation picture when we have the source and propagating the eigenstates of neutrinos. This is how we describe oscillations. And oscillations are driven by phase difference phase difference change between the eigenstates. And separation of the wave packets due to different group velocities leads to loss of the coherence. So one needs to take into account also a possible interaction with medium of neutrinos, which include vacuum expectation values, usual matter, condensates, classical fields, and possible new particles. Next, please. So this is landscape of recent studies, which includes various challenges to the theory, reformulations, improvements, corrections, changing of evolution equation due to Lorentz invariance violation, metric, etc. Oscillations at extreme conditions, low and high densities, low and high energies, dense neutrino background, etc. And of course, we are studying new interactions, non-standard interactions, long-range forces, etc. Next one. So in this talk, I will discuss mostly implications of recent experimental results, searches for sterile neutrinos, neutrino oscillations, and the standard model, and in the standard model, and neutrino oscillations and physics beyond the standard model. I will focus on the topics related to physics projects in Korea. I was asked by organizers. So namely reactor neutrinos, sterile neutrinos, and neutrinos interaction with light-dark sector. Next, please. So recent experimental results and applications. Next, please. Highlight of last year was discovery of CNO neutrino by Reno Experiment. And now we have 3.5 sigma evidence of existence of neutrinos from CNO cycle. And you see here very busy picture with different backgrounds. And the red one corresponds to CNO neutrinos. So one needs to overcome all these kind of additional contributions. So this is event number, and this is the energy in keV of events. So what is important is shown here. This is the CNO rate, essentially, and the experimental results are shown by this gray region. And there are two predictions from so-called high metallicity and low metallicity models of the sun. So first of all, there is, of course, agreement with data. Another important thing is that CNO flux is not suppressed. And CNO flux neutrino is in so-called intermediate energies where people were suspicious that maybe something happens, maybe there are some effects of new neutrino states or non-standard interactions. Conclusion from this that present data testify that there is no new physics in the intermediate energy range. Next, please. What has been essentially resolved is a solar cumulative tension in delta M square, mass square difference. There are a few new results. One is that super K now we see so-called upturn of energy spectrum, distortion which is expected from the standard MSW effect. The same seems to see SNO plus. Furthermore, the day-night asymmetry detected at super K is now lower from, it decreased from 3.3% down to 2%. This leads actually to higher values of delta M squared 2.1 extracted from the solar neutrino data. And now discrepancy between cumulus and solar measurements of delta M squared essentially reduced to 1 sigma. And you see here the picture. This is solar neutrino region in the plane delta M square 1, 2, sine square 1, 2. And you see here the cumulant result, and the disagreement is essentially disappeared. So it looks like there is no new physics behind this type of the tension. Next, please. So we have already discussed today by Hikawa-san this discrepancy between NOVA and T2K, and you see here the region for normal mass hierarchy from T2K, and this is from NOVA, and this is pi. And so these are the best fit values from NOVA, and T2K gives something like 1.4 sigma. So this difference is, say, 2 sigma tension, say. That makes some theoreticians to be nervous, and there are a few papers which discuss possible kind of better agreement between these 2 points, which actually uses the fact that NOVA has bigger baseline than T2K, and so some effects of sterile neutrinos or non-standard interactions can be important for them. Another interpretation is that if you make combined feed, that the combined value of CP phase is quite close to pi, which is kind of bad news for measurements of CP asymmetry. By the way, I should say there are a number of models which actually predict delta CP close to pi. So it doesn't mean that there is no CP asymmetry, there is no CP violation, but there is no CP asymmetry, say, in neutrino and antineutrino channel in this case. But we should follow the situation. Next, please. So this is global feed, which probably I will not discuss much. So the data are becoming more and more consistent. We have no now tension between solar and Kamlan delta M square. Delta CP is quite close to pi. And there's some preference of normal hierarchy, but not as strong as it was before. So next, please. Now sterile neutrinos. Next, please. Reno Experiment at Han-Bit nuclear power plant, which uses 6 reactors, made measurements of new E spectrum from unfolding of the data. And so they compared this with prediction from Huber-Muller model. The oscillation effects are subtracted using θ13, which we know. And so in this way, we get the spectrum at the reactor. Reno confirms the so-called reactor antineutrino anomaly. This is Reno result. This is the global result from all the experiments. And this flux is smaller than what is expected according to Huber-Muller model. And this is a quantification of this discrepancy. So next, please. There are some new results from Corchata Institute from Moscow, which measured the ratio between yields from uranium-235 and plutonium-239. In Huber-Muller model, the EU reactor experiment was used, and the data on inverse beta decay were inverted to the neutrino spectrum. And that led actually, after various corrections, to the deficit of the absorbed flux up to 10%. So the measurements of a ratio of yield of S5, which is for uranium 235, and the plutonium 239 is extremely important. New measurements made at Corchata Institute show what you see here. And so Corchata Institute sees smaller value of essentially yield from uranium-235. And it is smaller by precisely, say, 5%. That means that now if one takes into account these new measurements, essentially reactor antineutrino anomaly disappears. And you see here this ELL data divided by this 1054, and they are all in agreement. So it's not clear if these data are confirmed that this anomaly will survive. Next, please. So NEOS now uses the spectrum measured at at Reno, which makes sense because these are the same reactor, the same reactors. Before they use data from Daya Bay, and here you see comparison of the spectrum again from theoretical predictions and what you get from experiment using now Reno spectrum. This is for electrons and this is for neutrinos, and you see quite good agreement, although there are some wiggles. Next one. And these wiggles can be described by oscillations to sterile neutrinos with these parameters. Delta M squared 2.37 and mixing angle sine squared to theta 0.09. And you see this point here. And I should say that before, NEOS actually selected another value of delta M squared when they used Daya Bay spectrum. So that was the old values of parameters, and those are new values of the parameters. And you see kind of fragile determination, so that some changes actually lead to jumps of best fit point from one point to another one, which actually very much expected, because always fit with using some oscillations, which a priori not fixed delta M squared in mixing parameter gives better fit than without oscillations. And so always you will find some point of best fit, which you can interpret as oscillations. Next one, please. So there are new results from stereo and prospect, and you see they do not essentially testify for existence of sterile neutrinos and put the bounds. This is from stereo, and this is from prospect lines, and here you see the best fit from reactor neutrino anomaly, and this is the best fit from relatively new data from neutrino 4 experiment. Next one, please. So this is dance. They also do not see essentially oscillation effect and put these bounds on oscillation parameters. Dance experiment actually has a different value of best fit point, is 1.3 for delta M squared, and this value of sine squared to theta 1, 4. So we have spread of best fit points from different experiments, and I see this is kind of normal, and I should not insist on seeing any oscillation effect. Next, please. This is very disputable neutrino 4 experiment result, which actually testifies for a rather large delta M squared, and something like 7 electron volts squared, and a relatively big mixing 0.04. It was criticism concerned the energy resolution they used, and Monte Carlo simulations have been done, and even those data were kind of produced lower value of confidence from 3 sigma to 2.2, and of course the data from this experiment contradicts to other measurements as we discussed already. Next, please. So let me mention this new experiment, which actually starts in Japan. It started already and operates. And this is GSNS square, which is essentially, and you can see here what is actually explanation of this square. This is essentially a repetition of LSND experimental result, the first evidence for electron volt neutrino. And they will use muon decay at rest, and they will search oscillations of new mu bar to new e bar, the same as at LSND. So experiment started, and you see here the sensitivity of this experiment. It's given by blue line here. And simultaneously, recently, the collaborations produced a kind of new project of putting the second detector at a bigger distance. So the first one will be 24 meters, and the second one will be 48. And this red line is projected sensitivity when both detectors will produce a result. So next one. So neutrino oscillations and the standard model. Next one. One of the issues which I have selected is coherence and decoherence. You see, if you are working in X space, then decoherence is related to separation of the wave packets of the eigenstates due to different group velocities, and different group velocities due to difference of masses. In the energy space, the equivalent is just integration over energy resolution function in your setup. So you can consider the problem in both in X space or E space. And there is equivalence of two descriptions, which is actually based on the fact that the size of the wave packet in X space is given by inverse of the size of the wave packet in energy space. Group velocities, so one can introduce coherence lengths at which these wave packets will travel without separation. And this length is given by the size of the wave packet divided by difference of group velocities. Different group velocities are determined in this way. And in vacuum, we have difference of group velocities proportional to delta m squared over 2 energy squared. And therefore, the coherence length is given by this form. This is the size of the wave packet. And so this is energy squared over delta m squared. Next, please. So recently, in this paper, the authors have studied the coherence of reactor neutrinos. So the idea is the following. So if you have decoherence, it leads to averaging of oscillation picture. And the authors analyzed Diabay and Reno data. So this green line is without separation of the wave packets. And when you change the size of the wave packet, you will have increase. If you decrease the size of the wave packet, the coherence effect increases. So this is for Diabay and Reno, and this is for Kamland, which has bigger, of course, baseline, and therefore one expects a more this oscillatory picture. So the idea is that if you do not see the coherence effect, that the lengths between source and detector should be much smaller than coherence lengths, and that is transformed into a lower bound on the size of the wave packet. So analysis of the data lead to this result that sigma x should be bigger than 2 × 10⁻11 centimeters. It's not, it's quite difficult to predict the size of the wave packet, but so my estimation that it should be at the level of 10⁻⁹, maybe 10⁻10. So still this bound a bit weaker than what you can expect. Next, please. So the interesting issue is the coherence in matter, because in matter, the group velocities change, and therefore that leads to change of the coherence lengths. What is interesting then in matter with constant density, at certain energy, the coherence length becomes infinity, so that your wave packets will propagate without any separation for infinite distance in principle. Actually, this corresponds to the situation when group velocities in matter of the eigenstates are equal. So delta V is 0. And you see here how this coherence length in matter over coherence length in vacuum depends on the energy. So there is this energy E0 of infinite coherence. And then what is interesting, at high energies or high densities, in spite of large densities, the coherence length is as in vacuum. And it has some implications for supernova neutrino. Next one, please. So infinite coherence can also be not only in the constant density case, but in the case of periodic modulation of density profile, such that in half a period, one neutrino moves faster and another moves faster. So they kind of catch up each other. And so you can have a coherence for a very long period. So another example is so-called Castle-Wall profile when you have so-called adiabaticity violation. And in this case, one expects so-called parametric resonances. And you see here the probability as the function of energy. And you see at certain energies, this probability becomes 1. So these are the points of so-called parametric resonance. What is interesting, close to these energies, you have infinite coherence. So these are, again, dependence, or this is dependence of number of periods, coherent number of periods on the energy. And you see there are 3 points at which the coherence becomes infinite. Next one, please. So neutrino oscillations and beyond the standard model. I don't know how long I can talk, but this is the last topic of my presentation. So next, please. Next slide. So the setup is the following. We have standard model, and presumably there is a dark sector, which includes scalars, fermions, vector bosons, that is dark photons, sterile neutrino axions, myrons, etc. So interactions of neutrinos with this sector can be through so-called neutrino portal or Higgs portal. And as a result of these interactions, oscillations will be affected. So which means that with neutrinos and neutrino oscillations, you can probe properties of the dark sector. Interesting observation is the following. Refraction or refraction index, which is due to elastic forward scattering with Q square equals 0, is proportional to G square over the mass of the mediator square. So, which means that this V potential, due to matter effect, due to medium effect, doesn't disappear when G and M go to 0, in contrast to inelastic interactions when you have QG squared, this is coupling constant, over minimal momentum transfer squared. So this is restricted by observability, and therefore you can easily kill all these inelastic interaction restrictions, and still coherent scattering will survive. Next one. Well, this is kind of observation which people did already before, so-called resonance neutrino refraction. Actually, this resonance refraction, which means that you have enhancement of refraction index or potential, can be in the standard model due to Z and W bosons, but that happens at very high energies. This is actually, for instance, in the case of W boson, it happens in glacial resonance. So this resonance refraction can be at lower energies if you have new physics and light enough mediators, like you see here. So this is a possibility when neutrinos scatter on some fermions of background, and the exchange is due to some new scalar particle. So this is the resonance diagram. You have resonance associated with the mediator. So this is the second diagram. If you have some background with fermions, these were actually made the computations recently, then you can introduce asymmetry of background, and the results depend on asymmetry of the background, number of fermions and antifermions over the sum. The result of the potential, so this is what actually influences the neutrino oscillations, is given by this formula. It has 2 terms. One is due to resonance diagram, this one, another one due to this one. Now, V0 is proportional to coupling constant. By the way, I have forgotten to say that the simplest Lagrangian of interactions with dark sector is this one, and you have coupling constant, usual left-handed neutrino fermion, and this scalar, which actually corresponds to these vertices. Now, V0 is coupling constant square over mass of the mediator square multiplied by total number density of background particles. Now, one can introduce Y variable, dimensionless, which is energy over this resonance energy. And the resonance energy corresponds to Y equal 1. And that corresponds to total energy in the centrum of mass, as usually equal to the mass of the mediator. And in this example, this resonance energy is the mass of the scalar squared over 2 masses of the fermions. The width, and you see here the width of the resonance is given by G squared over 4 pi, and the mass of the scalar and this is dimensionless parameter. Next one, please. So similar systems have been considered before by Ge, Murayama, and then by the Korean group. So they also discussed the case of fermionic mediator and bosonic particles in the background. Next one, please. But the properties which I will discuss now are common for all these cases. So you see here dependence of the potential over V0 on the energy. This is why dimensionless parameter. So what is interesting, the behavior is that like this. You start from some value at zero energies, for instance, like this. Then the potential decreases. It reaches minimum. Then it increases, changing the sign, and then it decreases again. So there's a change of this potential in this way. So different curves correspond to different asymmetries. The biggest effect is when you have a asymmetric background, and that produces these outer lines. But it could be that there is no resonance diagram, and then you have such a behavior. For comparison, I also put here how the vacuum effect, vacuum potential, if you want, which is defined as delta m squared over 2 energies, depends on y. So this is just usual vacuum effect, and these are potentials due to interaction with the background. The relative contribution of the background and vacuum terms is given by this V0. Again, this is potential, which I have introduced before, over the value of the vacuum effect in resonance, so somewhere here. So that's kind of determine the strengths of new interactions. It's V0 over VR. Next one, please. So one can introduce the total potential, adding to the vacuum term also the background term, and you see here how this total potential depends on y, and you see here now, so the lines are shown in this way. If you include the matter effect and the usual matter effect, then you will have this line, and there are various crossings. I will not go into details, but so the inclusion of this background effect leads to substantial shift of usual MSW resonance in matter. You can actually test this using the Earth as the target. And some new resonances appear, which actually is interesting to explore how they work. One can introduce also the effective mass square in this problem. And this is defined as delta m square effective equals 2 energies. And this is the total potential, which includes vacuum term and the background. And this is given by delta m square in vacuum multiplied by this factor 1 plus VB over B vacuum. Next one, please. So introducing this potential will change the phase of oscillations. Actually, what is shown here, moduli of this delta m square effective over delta m square as function of y for different strengths of new interaction. And you see how dependence actually occurs. You have one at low energies, then it go to 0 and then go up because it's moduli square. Actually, the negative part is just turned, and then it has such a decrease. So the lines actually show somehow related to the baseline of the experiment, and the part of the curves above this line corresponds to quite big phase which can be observed. So for instance, if you have a long baseline experiment, the big phases are in this energy range and in this energy range. Next one, please. So tell me how much time can you give me? I have, say, 4 or 5 slides.
Okay, you can go ahead.
So now this type of resonance refraction actually has been used already to explain mini-Boone excess of events. So here you see again the probability, the oscillation probability, And in the simplest version, this background doesn't change mixing. It changes the phase because you add this V, new potential, which actually produces additional phase. Now, you see here this oscillatory factor, sine square phi is the phase of oscillations over 2, as the function, again, of energy. And what happens, using the previous computations, that this factor has the following behavior. It has a dip. It has increase in the resonance region. You see here fast oscillations because the phase can be extremely big. And then you have the tail at higher energies. Now, these plots correspond to different baseline of the experiment. And with increase of the baseline, you have wider region in which you have a strong effect of potential. So without additional potentials, you have these dotted lines, which you probably cannot see well. So this is the theoretical stuff, and then background excess was actually explained by this type of increase in the phase in certain range. So there is no effect here, there is no effect here, but if this resonance energy corresponds to 200, 400 MeVs, this is precisely the range where mini-Boone experiment operated, and that can explain the mini-Boone excess. Next, please. Unfortunately, this explanation doesn't work, and it doesn't work for the following reason. The point is that the effective mass of neutrino, which delta M square effective, depends on energy, as I explained. And here what is shown is dependence of this delta M square effective on energy when I put this resonance energy around 300 MeVs. This is what is required by LS&D result. So what happens is that you need to consider whole dependence of this mass in all the energy range. And if what you observe actually, that there is a strong difference between delta M square effective at low energies and at high energy. So for instance, let's take dashed line. So it has such a behavior at low energies, and this one at higher energies. So these are different experimental results which correspond to measurements of delta M square at different energies. These are reactor experiments, and T2K, NOVA, MINOS, IceCube, and Antares. So what mini-Boone requires is actually quite big R, which is, again, the strength of new interactions. Mini-Boone requires that R should be bigger than 1.6. And this is the line which actually corresponds to 10 times smaller value of R. So it's absolutely excluded by just data, by just strong dependence of delta M square on energies. And the best bound is something like R smaller than 1%. This is what is allowed. Next one. Probably I will be shorter at this point. So what is interesting that at higher energies, these potentials have behavior 1 over E, which is exactly the same as a usual kinetic term, which is delta M square over 2 energies. And I should underline that it is this 1 over E dependence which actually led us to the conclusion that oscillations, observed oscillations, correspond to neutrino mass. The question here is the following, that maybe one can just substitute the neutrino mass but by potential, which has absolutely the same dependence on energy. Here are some conditions for this, but you need light mediators for this and a light background particles. Next one. So what one can do, this 1 over E dependence appears when the energy is bigger than resonance energy. So the idea is the following. Essentially, we tested neutrino mass or 1 over E dependence, say, at energies above 0.1 MeV. This is actually what solar neutrinos give for us. So if your resonance energy is below 0.1 MeV, that in all observable range, you will have this 1/E dependence. And the question is, can we just completely substitute neutrino mass by this effective interaction? The problem may come from cosmology. And the point is that this mass, which we have introduced, actually depends on the density of medium. And if density increases, and it should increase in the past, like this, then effective mass actually also increases. And then you may get that, say, at the epoch of decoupling of CMB, your mass is, say, 100 electron volts, which is certainly in disagreement with data. Next one, please. So the problem can be solved again if one takes into account that this effective mass depends on energy. And here you see the dependence on energy of this effective mass. Next, please. And so what happens is that existing observations are here. Then there is this resonance, but then at lower energies, the effective mass decreases, which means that, for instance, if you take the energy of neutrino 10 to the minus 4 electron volt, then you can get that effective mass is 5 10 to the minus 6 electron volts. And even if you take into account this increase of the mass with Z, you will still satisfy CMB bound. For Reno experiment with energy 1 electron volt, the mass is, say, 2 10 to the minus 4 electron volt, which is unfortunately bad news. Then nothing will be detected. Next one. And this is my conclusion. Next one, please. So anomalies and tensions found in different oscillation experiments lose sigmas and disappear. So that's kind of overall assessment. In particular, the case of sterile neutrino becomes weaker and weaker. Standard oscillation picture holds. There is no deviation found, no new interactions observed, no dependence of oscillation parameters, masses and mixing on energy and time, and fundamental C conjugation. So actually, the search for dependence of oscillation parameters on energy is important way to search for new physics, in particular, interaction of neutrinos with new light sector. Possible interactions with light-dark sector are explored, and a neutrino oscillation can probe this sector. For very small couplings and masses, the refraction provides the most sensitive tests of this new sector. So resonance refraction at low energies can be observed if you have light mediators. And in principle, they can substitute usual neutrino mass by interactions with medium. There is no final conclusion in this last point. At least we can exclude mini-Boone explanation by studying dependence of delta M square on energy. Thank you very much.
Thank you. Thank you for the excellent overview talk on neutrino physics. Okay, so we are quite behind the schedule. So is there any question or comment? Okay, so let me ask you one question. What would be the effect of this neutrino interactions with the light-dark sector on the CPR symmetry in neutrino sector? So I'm just curious.
Yeah, you see, it can be adjusted in such a way that it doesn't change CPR symmetry. In the example which I have considered, this new sector even doesn't change the mixing angle. It changes the phase of oscillation, but not mixing angle. And now if you, of course, fix delta M square in such a way that it matches the experimental data, then there is no changes. I should say that we just looked at some examples. However, what one should do really to change position of this resonance energy and explore what are possible effects. So it is possible that in some situation, CP will be affected for certain parameters of this sector.
Okay, thank you for your answer. So,
And And I'm sorry for these problems which actually I produced.
That always happens. Okay, any other question? Okay, let's thank the speaker again for his nice presentation. Okay, so I think that's the end of this session. We'd like to thank